Sorry, with Irene, you are not.
Friday.
Thursday afternoon. Thursday afternoon. Not Thursday.
This day I was here.
Yeah, yeah.
Maybe.
But Irene, no.
Maybe I might go a little bit out and come. Okay. So, good afternoon, everyone. Welcome back after the break. So, a quick recap what we did so far. So, we discussed briefly about concrete technology, concrete mix design, the concrete testings, what are the properties and how they test in the laboratory or sometimes in the field. Okay, so that's we covered in the week 1. So then we did concrete design, RC, reinforced concrete design. That basically we look at RC beam and slab design before the break. So reinforced concrete beams and slabs. So when you work out, we discuss about serviceability limit state, ultimate limit state, when we should look at ultimate limit state combination, when we should look at the serviceability limit state combinations, and what are the checks will come under each limit state. We look at that one, and we also look at how to determine loads. Load means dead load and live load. put a separate video for the wind load, but we will study the wind load during other unit ENEC 20002. So I leave that wind load, but if anyone interested, you can look at the PowerPoint. Good. Then we look at the reinforced concrete beam, rectangle beam first. So when we have the rectangular beam, how to determine the ESD, the longitudinal reinforcement, and what are the checks we need to do. So the KU check, KU should be less than 0.36, and we also look at over reinforced, under reinforced, balance sections. What you mean by under reinforced section, what you mean by over reinforced section, what you mean by balance section. So those kind of things we discussed. Then we look at the shear, we also look at the minimum reinforcement requirements for rectangular beam. What is the minimum requirements? If it is a T beam, how to find out minimum. So those kind of things we look at, and we should be able to find out ESD, the longitudinal reinforcements required to carry the bending moment. Okay, so you may be able to use it, the formulas. You can solve the equations, or there are some charts available, so you should be able to do any of that methods. So then we look at the deflection, two different methods for deflection. One is simplified method, deemed to confirm method. So deemed to confirm method is quite conservative. They assume, they made some assumptions. So we use that deemed to confirm method in case if we don't know the depth of the beams or slabs, to check our assumed depth, because we don't need lots of information to find out the deflection using deemed to confirm method. Other one is a simplified method, more accurate one, but you need more information as well. So for example, if you want to use the simplified method, they said you have to use the effective I value, effective second moment of area. To find out effective second moment of area, you should find out second moment of area for cracked section, second moment of area for uncracked section. Then we also need to find out the shrinkage strains. So there's lots of calculations involved. So we look at what is cracked section, what is uncracked section, and the deflection case, because that's a serviceability limit state. So in the serviceability limit states, we assume or we consider elastic sections. Okay, so all the sections are within the elastic range. So we should be able to use all the elastic theories we studied under strength of material the undergraduate. Okay, so that means neutral axis will pass through the centroid, and parallel axis theorem for second moment of area. We should be able to use all these things. We also use the equivalent sections. We convert the composite section into one section. So we did everything based on the elastic theories. Okay. So then we should be able to calculate the effective I value, I effective using the equations given in the standard, and we should be able to use simplified method to find out the deflection. So deflection two methods. Similarly, cracks, actually three conditions. The first one is for indoor or interior structural members. If your member do not exposed to the environment, then crack control can be satisfied by checking the spacings between the reinforcements and providing minimum reinforcements. So it's quite straightforward and easier one. That's only applicable for the interior members. But if you have an exterior member, or if you want to calculate detail of the crack width, we have to use either direct method or indirect method for crack control check. Direct method means we straight away we use the formula to find out the maximum crack width in the member. So there is a formulas. You should be able to substitute the numbers and able to find out what is the maximum crack width. So that's a direct method. So you check the crack width. Sorry, you calculate the crack width and check it. But the calculation is quite low. Okay, so you need to find out the strain and everything using from the string gauge strain, creep and everything. So it's quite lengthy calculation, but that will give the crack width. Okay. The other one is indirect method. That is a little bit shorter or easier method compared to direct method. So in that one, what we do is we are checking the stress. We are checking the stress at the stress in the longitudinal reinforcement. Okay, we provide the longitudinal reinforcement. We find the stress in that reinforcement under service load. Okay, under service load, not the ultimate, under service load. So we can't use the simplified triangle method we use for the bending moments. Okay, we are considering serviceability limit state. So we should use the sections we use under serviceability limit state. So we calculate the stress in the longitudinal reinforcement, and if the stress is less than the value given in the table, so that is under control, so that's satisfied. So that's a little bit easier than direct method, or less calculation compared to crack width calculation. Okay. So those are things we discussed under the beams, and we also look at shear reinforcement calculation. So first we need to check whether the concrete can carry the shear force. If yes, you don't need any additional reinforcements. That will be the case for the slabs. Most of the slabs do not need any shear reinforcement. If you need the shear reinforcement, you need to find out if there is a maximum spacing and minimum shear reinforcement requirements. You need to also check that one. So that's all we did for the beams. When we discuss about, before we go into the slab, we also touch the TOL beams, T beams, L beams. Normally when we cast the concrete slab and beams together, you can't separate the beam and slabs. Okay? You can't separate beams and slabs. So you need to consider either T or L sections. So when you have something like that, your calculation will be slightly different because we have T section rather than rectangular sections. So especially when you provide reinforcement in the web area, bottom part, so you need to look at that one carefully. Okay. So in your project, all the beams, the beam you need to design should be T-beam, okay, not rectangular beam, because it's a bit slab and beams are cast together. So we had worked examples, tutorials and study guide both have worked example. Okay. If you have any problem, ask me. Then we look at the slab, and the slab we have two conditions: slab supported by beams or slab supported by columns, flat slab, normal slab. Okay. So if you look at the beam and slab design, almost same procedure. Okay. Different clauses, but still we look at the AST for the bending moment, minimum reinforcement and everything, shear, deflection, cracks and everything very similar to beams. Okay, in slab support by beams, normally we consider 1 meter strip, so the B is equal to 1 meter. Okay, in the rectangular beams, when you put the B is equal to 1 meter, that becomes slab. For flat slab, B is equal to width of the column strip or middle strip, in whichever you are designing. Okay, so we look at that one. I think I put all full workings step by step, and if you have any problem or couldn't understand any of the workings, please let me know. Okay, so full workings for flat slab, full working for the slab supported by beams, full working for beams including T-beams. So all these ones we covered before the break. So today we will look at the column. That's the other element in reinforced concrete structures. Okay. So what is the difference between columns and beam or slabs? If you look at the beam and slab, the main function, okay, main internal force in the beam and slab are bending. The beams are bends. So normally we don't have any axial force in the beams. Axial force means in the along the longitudinal direction. So we don't have any axial force, only bending. Yeah. So when you have bending, there will be a shear force. Okay. So that's normal. So when you look at I put the PowerPoint already, okay, but I will explain the steps. So when you have beam, you normally look at something like this. Yeah, beam have columns. So when you have loads, it's bent. Okay, so bending is the main.
Oh, sorry, it's not connected.
Oh, sorry. Yeah. So bending or shear. Okay, when you have bending, definitely there will be a shear force. Yeah. So that is what we look at in beams and slabs. Okay. So the loadings. So generally, when you look at the beams or slab, the loadings always comes perpendicular to the longitudinal direction. So we don't have any load, in that direction. Okay, we don't have any loads in the axial direction. But when you look at the column, so when you have columns, so you have, let's say you have beams or slab, whatever. So due to the beams or slabs, you'll have bending moment because it's rigidly connected. Okay. When you have rigidly connected, you have bending moment, and all the loads you have in the beams will give a bending moment, and also it will give an axial force. Okay. When you have bending moment, there will be a shear force as well. So generally, the columns need to be designed for bending, shear force plus axial force. So this is a new things we have under columns. Okay, if it is a bending moment and shear force, the design will be very similar to the beams. Okay, if it is only bending moment and shear force, the design will be very similar to the beam design. But now we have two kind of forces. One is bending, other one is axial force. So when you have a column, before we go into the design, let's look at the ideal case. When you have an axial force, something like this for a member, what kind of failure you can expect? What are the failure modes you can expect? If you have a member, you try to press that. Yeah. So for example, when you have a tensile member, okay, let's say you take a tensile member, you apply a tensile force. So what kind of failure you can expect? The member can fail due to tension. What does that mean? When you have a member, you apply the force. So when the stress in the member, equal or higher than the tensile strength of the material, it will fail. Okay. When you apply larger than or equal to the tensile strength of the material, it will fail. So that is tensile failure. Okay. So we have a compression force. When you apply compression force, there will be some area. Yeah. So the stress is equal to force upon area, isn't it? Yeah. So when it is equal to the allowable stress, or allowable strength, it will fail. Okay, so this is called compressive strength failure. It is compressive strength failure. So when the stress we apply equal to allowable or maximum or ultimate stress, whatever, it will fail. So that is very similar to other members. If it is a bending, when the bending stress equal to maximum bending strength, it will fail. If it is a tensile member, when the maximum stress equal to tensile strength, it will fail. So that is very similar. This is called strength failure. Okay. The other one, for the compression members, we have another type of failure that is called buckling failure. Buckling failure is only happen in compression members. Okay, so the Euler critical load is defined as a pi squared EI upon LE squared. Effective length squared. This is effective length. We'll come to that effective length in a minute. Okay, but this is called Euler critical load. They named those who derived that formula. So what does that mean? When your force reach to, when the force P reach to the critical load, it will fail due to buckling. So we have two types of failure. Okay, we have two types of failure. The first one is strength failure, second one is a buckling failure. So these two types of failure, both are different, and that's only happen in compression members. Okay, we will not see buckling failure in tension member, we will not see buckling failure in bending member. It's only happen in compression members. So we need to make sure our member is safe from both of these failures. Okay, so if you look at this one, I will rearrange this. P is equal to pi squared EI. This is the maximum. I is the second moment of area. Second moment of area, A R square. This is called second moment of area. R is called radius of gyration. Okay, so that is the, I'm explaining these ones based on the strength of material. Okay, we haven't gone to the concrete design yet because this understanding is important. So I'm going to substitute P is equal to pi squared AR squared LA squared. So if you pi squared EA, if you bring the R down, LE upon R whole thing square. Okay, so if you bring the R down, so it will be LE upon R. So LE squared upon R squared. So it's same equation, not change anything. So pi square EA, you put lambda square, lambda is equal to LE upon R. What is LE? Effective length. This is called slenderness. Slenderness. Okay, SL. Slenderness, same word. Slenderness. same word. Slenderness, lambda is equal to LD upon R. So you can see effective length is a kind of a length of the member. Okay, R is radius of gyration. When you have a larger cross section, R will increase. Okay. So if you look at this, if I draw the graph, this is lambda, this is P. Okay, this is lambda, this is P. So P, we had two conditions: strength failure this one. So P is equal to sigma allowable times area. Buckling failure, here P is equal to pi square EA upon lambda square. So if you have two, I'm going to draw the graph P versus lambda. Okay, so this is y-axis, this is in the x-axis, lambda. Yeah, so it's a inverse proportion for the square. Okay, inverse proportion. Yeah, so what is the shape of the graph? What is the shape of the graph? So you will see something like this if you plot the graph for buckling failure. So for buckling failure, for the strength failure, P not depends on lambda. No? It is not dependent on lambda. For whatever the lambda doesn't change. So for strength failure, it's a straight line. So for strength failure, buckling failure. So you can see this point up to this point from here, the strength failure is less. Yeah. So that means the buckling capacity is larger, strength capacity is small. Yeah, up to this point. Up to this point, strength failure values are less. So what will happen when you increase the load? It will reach strength failure first, then buckling failure. Okay. So in this region, up to here, you will get the strength failure. Yeah. From here to there, the buckling capacity is less, okay, compared to strength capacity. So in this region, in this range, when the lambda from here to there, you get the buckling failure. Okay, so we have we had two type of failure. when you have smaller lambda, lambda is this one, okay? When you have smaller lambda, you will have strength failure. Yeah? When you have larger lambda, you will have buckling failure. So this is the critical value. Okay. So here we call short column. Here we call slender column. So slender column means you have buckling failure. Yeah. Short column means you will have strength failure. So we need to understand the column. If you have a column, depend on the lambda value, it can be a short column or slender column. Okay, slender column means buckling is a criteria, failure criteria. Short column means strength value. Which one is you think is better? Always buckling is very danger. Okay, buckling failure is quite danger, and you also can see the drop in the capacity is quite significant. It's a parabolic. Okay, if it is a straight line, it's different, but it is parabolic. When you have larger lambdas, the drop is very high quickly. Yeah. So we will see the short column is better, but that doesn't mean you can't do anything with the slender column. Okay, you can do that one, but short columns are better. So this is the basics of the column design. We will see how to do that one in concrete. Okay, so this up to this part. All these theories, basic theories, is valid for any columns. It can be steel, it can be timber, it can be concrete. Okay, this is strength of material theory. Okay, so it's true for any cases. Now we will see how to handle the concrete one. Okay, so when you have a concrete columns, so let's say you have multi-story buildings. Okay, so let's say you have a multi-story building. Yeah, so each levels, just draw something. Okay, so if I want to design this column, generally when you design the column, you need to design the bottom part, because when you have loads here, so this will transfer half to this side, half to that side. Yeah, so we will have some axial load and also bending moment in this place. Yeah, so then as we go down, axial load will increase because self weight of the column will be added as we go down. Yeah, so here almost very small self weight because only this much of length. Here this much of sulfate. Yeah, so sulfate of the column will be added, so your axial load will increase. Yeah, so if you draw the graph, axial load, so here almost zero, very small, then it will increase gradually. The increment here is due to sulfate. Then this flow load will be added. Yeah, so here you have some loads. Yeah, so half load will go there. Yeah, so you will have a sudden increase here. Then again it will go like that, increase and further. Okay, so this one come from flow, and this one due to sulfate at the core. Yeah, so axial load will increase from top to bottom. So generally the bottom column, this one, will get largest axial load, isn't it?
Yes.
So because that all the flow load will come here, and all the sulfate will come there. So we need to design this column. We need to design this column. So if you apply all the loads, you might get some bending moments. Okay, it can be something like this, bending moment diagram. Okay, so when you have bending moment like this, how to mark the moments. So this is say 24. So let's say you analyze this column, or you analyze the frame, and you get something like that. So how to mark this bending moment here? When you put this bending moment this side, this is the tension side. Okay, so your bending moment will be like this. Okay, so always the values are marked on the tail side. So here the bending moment is looks. So here 250, here 300. Okay, sometimes you might get the bending moment diagram something like this. Okay, in that case, mark this way. So okay, so we may have two different bending moment diagrams, either this or this. So this means bending moment like this. So if you look at this one, we put the bending moment like this. Okay, so if you take a ruler, and if you take a ruler and if you apply the bending like this, so this will bend. Yeah, it will bend like that. If you apply one moment this way and another one that way, so it will bend So this is called double curvature. Single curvature. Okay. So when you have bending moment diagram something like this, it's a double curvature. When you have bending moment diagram something like this, it's a single curvature. It's depend on that the effective length will change. Okay, so let's say this is the effective length. Okay. So when you have double curvature, actually your beam bends like this. Okay, so your effective length will be more or less half of that. Okay, nearly, not exactly. When you look at that, this one with the double curvature, your effective length will be half compared to this one, because it's bend or buckle for the whole length. Here it will buckle or bends for the half length. Okay, so when you have less effective length, you will have less lambda value. Less lambda value means it become short columns. It's much better. Okay, so when you have short columns, you may end up with the smaller dimensions and smaller reinforcement. If you have if you have single curvature, you'll end up with the larger dimensions, because single curvature means larger effective length. Larger effective length means larger lambda. Okay, so that is important. So depend on the connection for the other members and the loadings, you might get either this or that bending moment diagram. How to get the bending moment diagram? You might use the approximate analysis methods. You might study some approximate structural analysis method in your undergraduate analysis of structures unit. If you haven't, you may able to use the software. Okay, I think in the week 2 or week 1 I put a link, Space Gas, isn't it? Did I put? Is it there? Anyone? Space Gas link is there? Should be there, isn't it? More.
check.
Can someone check that one?
So there is a space gas introduction tutorial at week 2.
It is there?
Space gas introduction tutorial for week 2.
Yeah, so you also have there is a link it's given, it's not?
Yeah, it's there, sir.
Yeah.
To
So-
register?
Sorry?
To register.
Yeah, so you need to click that link, and then you should be able to, if you send that form, it will bring to your phone. You need to put your details and email address, and they will send a link to download the Space Gas student version. So free, you don't need to pay anything. Okay, download it, and I think in week 2 I explain how to use that one. Okay, you can use any software, that's not a problem. Okay, and the Space Gas website also have lots of training things, but you don't need to do all complicated works, only model your structure in the Space Gas to get the bending up. Okay, it's quite straightforward. You don't need to spend lots of time to get that model. If you are not sure, we'll talk about tomorrow in the drop-in session, the workshop time. Okay, so what we need is we need to get the bending moment and axial force values. Then we should able to decide the required steel. That's what we are going to study. So when you have a column, we need to design this one, okay, the bottom part. Even though you asked to design the whole column, generally we look at the bottom part so that it will give the largest axial force and also bending moment. So when you have something like this, now the question is, okay, I have the bending moment diagram, I have the axial force diagram from space case. Okay, how to analyze the column and find out the steel requirements. So if you want to find out the steel requirements, the calculation is a little bit different from what we learn for the beams and slabs. Because in the beams and slabs we have only bending. Here we have two actions. So we need to develop a diagram called interaction diagram. Okay, so M star versus N star. Or sometimes they use M star upon BD squared versus N star upon BD. Okay, so this is called normalized interaction diagram. This one is a normal interaction diagram. Okay, so we will see how to develop this one, interaction diagram. So that means we need to develop an interaction diagram, that is a relationship between bending moment and axial force. Okay, that is the relationship between bending moment and axial force. So the diagram looks this way. Okay, so if you develop the diagram, so you'll get something like this. Okay, you'll get something like this shape. If you draw the interaction diagram for a given section, you will get something like this. Okay, to draw this diagram, you should know how to draw this one. To draw this diagram, you should know at least the 4 points. Okay, you should know these 4 points. So there are standards. Give me a second, I will bring the standard PEM. So section 10, okay. This is the diagram. These are the important 4 points. First one is called scarce load, decompression point, valence point, the pure bending point. These 4 points are critical to draw the interaction diagram, that is N star versus M. So we need to know what is each point means and how to get those points. If you have those points, you should be able to develop your diagram. Okay, so there are standard diagrams available, but as a part of this unit, you should know how to develop this diagram. So we will see one by one. How to find out, determine those points. Okay, and they also give the clauses, relevant clauses. Okay. So the first one is scarce load, that is here. This is point 1, point 2, point 3, point 4. Okay. I think I provided the study guide, isn't it? The study guide is given, isn't it, for these columns? Under week 6, I think, or week 5. Yeah, under the week 5, there's a study guide. I explained the whole things step by step. I'll explain now, but the full workings are given under the study guide. Okay, so the whole step by step explanation is given, but I will explain now that if you need some fine readings, look at the study guide. Okay, what is scarce load? So here there is no bending. That means only axial load. Okay, no bending, only axial load. So there is no bending moment. Okay, so you have this one. This is B. Here in columns we will provide the reinforcement generally in all four corners. Okay, generally we will provide reinforcement in both corners. So this is ASC, AST, okay, so both are equal. AST, ASC, that is equal to area of steel by 2. Half the steel will go the tension side, half the steel will go to compression side. Okay, here remember the standard notation still works. This is small d, this is DSC, the whole area, the whole depth is capital D. Okay, that is capital D. So now we apply, this is a little bit different from what we did under the beam. So here we are going to apply a force, axial force. Actually I applied perpendicular to this. Okay, here I use NUO. Okay, remember we applied perpendicular to this plane. Okay, I can't show that one, it is something like this. Okay, NUO is applied here. NUO is applied here. So here there is no bending, only axial force. When you apply only axial load, there is no bending, means the strain diagram will be something like this. That is strain distribution. Okay, that is strain distribution. Because no bending means you only apply axial force, the whole cross section is under compression only. Okay, the whole cross section is under compression only. So you have only compressive strain, there is no other issues. Okay, if it is a bending, only one place tension, other place compression. Okay, but here only pure compression. So in the standard, the close 10622, this is the close related to this one. They said the maximum strain in the compression should not exceed 0.0025. Remember, for beams, that is when you have bending moment, we said maximum strain can go up to 0.003, but it is 25, little bit less. Under pure compression, it cannot exceed 0.0025. Okay. So if you have pure compression, okay, this steel also have same strain, this steel also have same strain. Concrete strain is equal to 0.0025. 0025. Since it is only compression, the whole section will have same strain equal to 0.0025. For steel, we use N-type bars. So when you have N-type bars, the yielding strain is equal to 0.0025. Okay, so when you look at this one, the whole section is 0.0025. So both steel, okay, both steel means compression steel and tensile steel, both steel will reach the yielding point. Okay. What does that mean? Compression reinforcement stress is equal to Fsy, yielding stress, Fst also Fsy. Both are the yielding point. Okay, so we need to find out the forces. Yeah, this is strain distribution. If you have strain distribution, where is the neutral axis? Where is the neutral axis? Is there any neutral axis here? In this one, we have only compression. What is a neutral axis? When you have zero strain, this is a neutral axis. When you have zero strain, you have neutral axis. But in this case, no zero strain, everything is same. So our stress distribution is not like this. It will be, it's going like that. So we will not get any neutral axis here. So neutral axis will be somewhere in infinity. Okay, so dn, yeah, at infinity, very large, because it's the same, it never goes like this. Yeah, so it goes like this, so it's never touch this axis to zero. Yeah, so this is the zero strain if you have. So neutral axis will be somewhere in the infinity. So our stress block will be like this, approximate stress block. Here in bending we said is alpha 2 F dash C, isn't it? This one, stress block alpha 2 F dash C. Here alpha 1 F dash C. Okay, alpha 1 F dash C. So if you have something like that, there will be an FC. So FC is equal to alpha 1 F dash C uniform stress. Yeah, uniform stress. Is that correct? And this much of area times BD yeah, is that correct? Same stress area, but here these two areas are belongs to concrete. I will take that one, ASC. So what is this one? Plus ASC, the stress is equal to FSY, plus AST, over there also FSY. So alpha 1 F dash C BD AST ASC both are equal, both are AS by 2, half of the steel. Okay, half of the steel, half will be here. So total steel is AS, half will be tension, half will be compression. So half plus half minus AS plus this also same, I put AS FSY. Okay, we'll have some force here. Everything compression, even though that we put as a tensile steel, currently everything is under compression. There is no tension in the section, even though we call this a tensile reinforcement, compression reinforcement, but it is everything under compression now. Okay, so if we just rearrange this one, sorry, this is not, my apology, sorry, this one is correct, this is FC, sorry, my apologies, this one is correct. FSC is equal to ASC FSY, FST is equal to AST FSY, sorry, it's not adding. So this is FC is equal to stress time area of concrete, stress time area of concrete. This is force in the steel, stress times stress, force in the other steel, area time stress, sorry for that. So these are the forces acting here. There are three forces, concrete, stress time area, compression steel, stress time area, tensile steel, stress strain area. Okay, these are three forces we get from steel and concrete. Why we get this force? Because of this axial load. So axial load NUO is equal to FC plus FSC plus FST. Everything is compression. So when you apply this one, we get this one. So alpha 1 F dash C BD minus AS plus ASC FSY plus AST FSY. This is AS, so alpha 1 F dash so this is NUO. If you rearrange, you will get NUO alpha 1 F dash C BD plus AS times FSY minus alpha 1 F dash C. So this is NU. Alpha 1 is given in the standard. They gave what is alpha 1. The standard they gave what is alpha 1. Alpha 1 is equal to alpha 1 should be between 0.72 and 0.85. So this is alpha 1. So this is NUO. So this is the maximum axial force the column can carry. Alpha 1 is given. F dash C is, you know, the strength of the concrete. B and D, size of the column. And you should be able to find out what is NUO if you have a particular AST. Okay. So generally in columns, AS area of steel is between 1% and 4%. So this is the maximum and minimum steel area in the column. When you design a column, you cannot exceed 4% of the total area, or similarly you cannot go less than 1%. So what normally we do is we will develop an interaction diagram. Okay, there are some standard interaction diagram. You should be able to develop an interaction diagram for 1% steel, 2% of steel, 3% of steel, 4% of steel. So we will get something like this. Say 1% of steel. So for the different steel, we will develop the interaction diagram. So if you have that standard interaction diagram, then you should be able to design. Okay. So we will see how to design, but first we need to know how to develop the interaction diagram. So to develop the interaction diagram, we need the 4 points. The first point we already discussed. Okay, first point we already discussed, NUO. Okay, so what you need to do is you'll assume 1%. So if you have area of the column, so let's say 400 by 400 column, 1%, so you can say if the column is 400, this is B, this is D, so you can assume 1% steel is AS is equal to 1600, 2% AS is equal to 3200. Like that, you can take steel. For each steel values, you should be able to develop the interaction diagram. So that means you should be able to find out NUO. So if you know the B and D and AS value, 1% of steel, you should be able to find out the NUO. All the values are known. All other values are known. So you will find out NUO for 1%, 2%, 3%, 4%. So then you should be able to develop this diagram one by one. Okay. So now the second point, how to find out second point. The second point is called decompression point. So now, earlier one cast load, we don't have any bending moment. Okay, we don't have any bending moment. So if you don't want to have any bending moment, technically we should apply the axial load at the centroid. Okay, we should apply, isn't it? We should apply our axial load. We should apply our axial load at the centroid. If you apply the axial load at the centroid, you will not get any bending moment, isn't it? Yeah. If you have a cross section, let's say this is this one. So if you apply at the middle point compression, so you will not get any bending moment. But if you apply somewhere other than this centroid with an eccentricity, there will be a bending moment. Okay, so at the scarce load we apply at the centroid. Okay, then we are going to move the applied load. Okay, so centroid, no bending. Little bit up, so there will be some bending, yeah, because of the eccentricity. If you have more and more, if you move away, moment will increase, yeah, moment will increase. Okay, so little we will move away from the centroid. So we introduce the bending moments. Okay, we introduce bending moment little. So here square slope, no bending because we apply at the centroid. We little bit move up, So we'll have compression here, we'll have tension. So we try to move a little bit up. Okay, so move further, some extra moment, something like that. Okay, so here the strain distribution will be like this, and then strain distribution start to move like this. Okay, so the strain distribution from the parallel line, so we're moving slowly, 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 moves like this. So that's what we are going to do for the decompression points and the balance point. Okay, so we slowly move the axial load, we slowly move the axial load, we slowly move the axial load away from the neutral axis or centroid, then it will give the bending moment. Okay, so let's say what is decompression point means. So they said at the decompression point, so let's say this is a centroid and we applied somewhere there. Okay, so this is an eccentricity. This is the eccentricity measured from the neutral axis. Okay. So now we are going to find out where we are going to apply this axial load. Earlier at the neutral axis, now we'll see. Now it is the decompression point, the definition. What is the definition they said? They said decompression point means this is the compression side, because when you apply, this is the tensile strength. Yeah. So they said, if you read that standard, they said at decompression point, the extreme tensile fiber here. This is compression fiber, this is tensile fiber. Okay, so extreme tensile fiber will have zero strain. Okay, so the strain distribution here 0, you'll have some compression strain. So the strain distribution, and they said it is 0.003 as normal. Okay, only for the cast load it is 0.0025. In all other places we will use 0.003. Okay, so we have the reinforcement, compression reinforcement, tensile reinforcement, So we have some strain here. Okay. Is it clear? So where is the neutral axis now? So in this case we will have a neutral axis because this is the neutral axis. Neutral axis means where the strain is equal to 0. So this is the neutral axis. So actually the tensile part, the full looks like this, yeah? But we don't have anything below. So this is the neutral axis. So the neutral axis depth is equal to capital D. Yep. This is the dn, isn't it? dn we measured from the compression side. If you remember the beam things, we measured from compression side to the neutral axis. Neutral axis means zero strain. Okay. So under the scarce load, dn is equal to infinity. Okay, because we don't have the neutral axis in our diagram. Both lines are parallel. Constant strain distribution, so the neutral axis distance will be quite large. Okay, it's infinity. Now it is dn. So above neutral axis everything under compression, below neutral axis it will be tension. So neutral axis is here. So below the neutral axis is tension. So nothing below the neutral axis. Above the neutral axis, whole section is above the neutral axis. Yeah. Whole section is above the neutral axis. Everything under compression still. Okay. Everything under compression because neutral axis is at the bottom line. So whole section including tensile reinforcement, everything under compression zone. Okay. So neutral axis dn, the rectangular method, yeah, this is what is that, gamma dn alpha 2 f dash c, alpha 2 f dash c, gamma dn. So you'll have an fc here, and due to this steel you'll have fsc, due to this you'll have fst. Okay, I don't know whether it's fst is here or there, but there will be a force. Okay, any questions so far? Yep.
I'm not sure.
Lots of question, lots of calculation.
Yeah.
Okay. So the whole working is given in the study guide as well. Okay, step by step. So now I need to write the equation. So Fc, same area, sorry, same uniform stress, alpha to F dash C. Okay. Yep. Area of steel. So area of steel B times gamma dn. But I will take the area of compression ASC. FSC steel, this one, FS times ASC. At the moment I don't know whether it's FSY or not, okay? If the strain is equal or larger than yielding strain is equal to 0.0025. Yeah, for yielding strain is 0.0025. If the strain is larger than 0.0025, then the stress in the steel will be FSY. Otherwise, this will be like this. Okay, so I'll put FSC. FSC can be like this. Similarly, FST in this case it is very small. Okay, you can see this is very small strain, so most likely we will get this one. Most likely we will get this one. This will not reach the yielding point. This is very small. But this one we don't know. This is 0.003. Depend on the distance. It can be 0.0025 or less. We don't know. Okay. So to find out this one, we use the similar triangle. So similar triangle, E, the strain divide by that. This distance, D minus DSC, the whole one is DSC, sorry, whole one is D, this is DSC. So the whole distance depth is D minus this one, equal to 0.003, the whole. Similarly for this one divided by this, D minus small d, so you should be able to find out the strains using similar triangle. using similar triangles, you should be able to find out the strain. If you have this strain is larger than 0.0025, then that is FSY, otherwise strain times E value. So I should be able to write the NUD, the axial force. Axial force is equal to FC plus FSE plus FST. So if you add these three, you will get NUO. Oh, sorry, NUD. Now I need to find out what is eccentricity, because I need to find out bending moment. Bending moment is equal to force times eccentricity, because if you apply the axial load at the centroid, you will not get any bending moment. If you apply with eccentricity, the bending moment is equal to applied force times eccentricity. So bending moment MUD times E. So this one is there. I need to find out E value. I need to find out E value. I need to find out E value. Yeah. So the bending moment is due to eccentricity. So we don't have any other bending moment. So for the equilibrium, I am going to take the bending moment about this point. So this one times this distance, I'm taking, you can take the bending moment about any point, but this is easier. So this one times this distance plus this one times this distance equal to this one times this distance, this one times that distance, that is equal to that moment, this value times this distance. Okay, so this is the system, this is the resultant. So I need to take the bending moment about this point for that force, that is equal to this one plus this one. So NUD from here to there. So I mark this one as a GD by 2. Okay, I mark the half distance as a GD by 2. The whole distance I put as a GD. Half distance GD by 2. So GD by 2 plus E. So that is the bending moment from the applied force about the tensile reinforcement. So I am going to find out the same thing here about this point, FC times that distance. From here to there, small d, minus from here to there, half the gamma dn. From here to there, small d, from here to there, half gamma dn. So that distance will be the d minus gamma dn plus FSC from here to there, small d, from here to there, DSC So you should be able to find out all other values are known. FC we already have, FSE everything we have. Only E is unknown. Find the E from this equation and substitute here. You find out E from here and substitute here. Okay. So this is how we work out the decompression point. The next one is a balance point. The same work, but the stress distribution is slightly different. So I will explain that one tomorrow because it's the link will disconnect in 2 or 3 minutes. Do you have any questions so far? Please go and try this one. In the exam you should be able to find out. At least 2 points: decompression, scarce load, balance point. What we said for the exam, class test, it's open book or closed book? What we said.
So before exam, I have different question other than exam and class test.
Open book, sir.
Do we have any software analysis later on?
Sorry?
Software analysis.
Software analysis.
We have later on
For what?
for the whole system like beam or column.
Yeah, how to use the space gas.
Yeah, something like that.
Yeah, so I put a video there. Have you seen that one?
No, sir. I'm not talking about that one. I'm talking about later on. Do we have any software analysis?
No.
for the whole system?
Other than space gas, no software.
So can you come again?
Other than space gas you use for the columns, there's no other softwares.
So that's the only part we will learn on this unit.
Yeah, there's no, this is a design things.
Okay, sir. Okay, sorry.
Other one is a pre-stress. From next week we will do the pre-stress. That's a different design. This is different design. The software will help to find out moments and others.
Okay, sir. Okay, sir.
I'm not sure what software you mean. If you want any software, just let me know. I'm happy to explain. But the first we need to cover the fundamentals.
Like in bachelor, we did ETAPS and STAT Pro. So we have something like that, like for the whole structure.
So which software?
So ETAPS and STAT Pro. It was in our bachelor.
Yeah, but they use a different softwares. Because each software, the strand 7, those are analysis softwares. Yeah,
So I'm talking about the analysis software. Is there any software like in bachelor we did?
Yeah,
ETAPS and
analysis
STAT
software.
Pro.
There is another unit for the analysis software that is called finite element something. There is an elective unit.
Okay.
Okay.
Okay, sir. I got it now.
So normally in these units we will cover the design softwares. I think space gas will be detailed covering under the other unit as well. Because this one has lots of design standards. So lots of design standards, something like AS3600, quite lengthy. So that's why we don't put any others. So the space gas will be